Okay, welcome to the first in the next series of physics videos. We're going to cover speed, distance, time, which was one of the videos that wasn't covered last time. And over the next 45 minutes, we'll hopefully cover the whole content that is expected of you to learn ready for your Year 11 exam. And we'll start with looking at some of the syllabus for speed, distance, time. And if you see, the first three things is motion, using terminology such as speed, velocity, and acceleration. The equation for speed and the equation for acceleration. Those are the first three we're going to look at in today's session. And then later on, we'll look at the graphs and how we can use graphs to also understand speed, velocity, and acceleration. So looking at speed, first of all, the first thing is understand that speed is a distance traveled per unit of time. What that means is something as simple as a vehicle traveling 1 meter per second implies that in 1 second it has traveled a single meter. Similarly, a vehicle traveling 5 meters per second, that's why we write 5m/s, indicates it's traveling at 5 meters per second. If we look at a larger time frame, such as a vehicle on the bottom traveling 12 meters in 2 seconds, what would you expect that speed to be in a single second? So look at those three options. Hopefully you can think of it before I click it, but it should hopefully be 6 meters per second, because a vehicle that travels 12 in 2 seconds is the same thing as saying 6 in 1 second, so 6 meters. If we wanted to calculate speed, we would use the equation. So this is one of the things we want to look at now, is focusing on exam technique. Make sure you choose the correct equation. In your exam, you'll find them on page 2. And speed is equal to distance over time is the equation we would look for. So your first step in any GCSE question is look at the correct equation, look at what you know, look at what you don't know. Once you have the equation, you'll plug in your numbers. And in this example, we have speed is equal to distance over time, and our distance is 100 meters, our time is 5. That's why 100 divided by 5 is equal to 20. But remember units, so 20 meters per second. So a good exam technique is always to focus on the steps, choosing the equation, inputting the correct numbers, and answering with the correct unit. So if you feel confident with the speed equation, the next part is to understand, well, speed is a measure of distance per unit time. And notice how we can describe a vehicle that's going from left to right as being 5 meters per second, or a vehicle going from the right to left as being 5 meters per second, because speed is something we call a scalar measurement. It only has a size, a value. It doesn't have a direction. So you could be going towards something or away from something, but the speed is always a value. Velocity, on the other hand, has not only the size, but it also has the direction. So in this example, if we look at the screen, we could take the left as being the negative, we could take the right as being the positive. And in this example, the velocity of the red car is plus 5 meters per second. However, the velocity of the blue is minus 5 meters per second. It doesn't just have to be plus and minuses. It could be north, east, west, south. It's just understanding that velocity is a vector. It has a direction and a size, whereas speed only has that size. It only has a value and not quite the direction. So speed, very straightforward. We understand the equation. If we want to look at acceleration, so now we take that speed and we want to look at something that has a speed which changes, we can understand the different types of acceleration. First of all, what if a vehicle starts at one speed and ends at the same speed? That would indicate the acceleration is 0. So that means there's no increase, there's no decrease in speed. However, an object that accelerates from a low speed, for example 0, and increases to 20 meters per second, we would say it is accelerating, because from left to right, the velocity has increased. So there's a positive increase in velocity. If an object from the left to the right starts at a high speed and finishes at a low speed, we would say the object is decelerating. The vehicle is decelerating because the final velocity is less than the initial velocity. We can represent this better in an equation, which is always useful in physics, and the equation I'd expect us to use is acceleration is equal to the change in velocity divided by the time. The one thing you need to remember, though, that can be slightly problematic, is if you get change in velocity wrong. The change in velocity is that final velocity minus the initial. So you always have to remember it's the final velocity first minus that initial velocity. So if we look at the red car, it begins at 4 meters per second and reaches a final velocity of 20 meters per second in 4 seconds. So if you want to take a moment to pause the video, if you're watching this back, you can try the questions yourself. If you're watching it live, hopefully you can get the answer before me. But for the red car, the change in velocity is going to be positive, 20 minus 4, which when you divide that by the time, you get an answer of 4, because 20 minus 4 is 16. However, a car on the right goes from 15 meters per second to 0 in 3 seconds. It's very important that you understand that you get the correct way round, the 0 minus 15. So why is the answer minus? It's because in this case, the vehicle is decelerating. It is slowing down. Good, so far so good. We now have a better understanding of speed, velocity and acceleration. Using those terminologies, I'd like to think you can describe what speed is, what velocity is, and even be able to differentiate between speed and velocity and describe how they are different. Using your definitions of speed and velocity, you should be able to define acceleration and how it depends on velocity and not speed, and then comfortably use the equations for speed and acceleration. If you're doing higher tier, you should hopefully get some appreciation and develop a skill set for rearranging these equations. But overall, I think of those three, very quick and easy. We've gone through the 2 equations and the terminology. Best thing for us to do now is look at some practice questions where we put it all together to help us understand. Question 1, if you're working ahead of me, feel free to put the answers into the chat. If not, if you are watching this after it's been live, pause it so you can work ahead of me anyway. So question 1, if a truck travels 2,000 meters in 125 seconds, use an equation from an equation list to calculate the speed of the truck. So hopefully in some of your notes from physics, you have the list of equations for year 11 and you pull out speed is equal to distance over time. And a good practice here is identifying your numbers. So remember, step 1, identify the equation. Step 2, use the numbers. And step 3, you get the final answer. So speed, distance over time, input 2000 divided by 125, and you get a speed of 16 meters per second. So what that tells us is that over that distance of 2000 meters, the truck traveled at a speed of 16 meters per second. The higher tier only question is where we actually need to use our skills of rearranging the equation. So for this one, we need to look. If the truck continues at the same speed, which implies we need to use that speed we just calculated, for an extra 40 seconds, what distance would we travel? So hopefully in the next few physics sessions, one of those sessions are going to cover equation triangles, which will allow you to feel more confidence in rearranging equations. But for now, we can look straight away. Speed is equal to distance over time. So distance is equal to speed times time, if you can rearrange that comfortably for higher tier. Using the 16 meters per second we calculated earlier, the 40 seconds is from the actual question. and we get a new distance of 640 meters. That's not the final answer, because in part A, the vehicle had already travelled 2,000 meters, which means you have to add them together to get a total distance travelled of 2,640 meters. So this is a good example of part A, foundation tier style, using the numbers, choosing an equation and getting a correct answer with correct units. Higher tier, first little hint there, you had to rearrange your question. Another practice question now, looking at the acceleration equation. What is the acceleration of a racing car if it accelerates from stationary to 36 meters per second in 3 seconds? So straight away, one thing that should stand out is terminology. The word stationary should hopefully hint that it implies it's at rest or at 0 meters per second. So when you see the word stationary, you should hopefully think that means 0. So acceleration is change in velocity over time. So if we are looking for our change in velocity, we now can see straight away it reached a speed of 36 from 0. So our change in velocity is going to be 36. If we choose the equation, input the numbers, get an answer of 12 meters per second squared. So that means the acceleration is constant at 12 meters per second squared. Higher tier, again, it's a skill where you have to rearrange. How long will it take for the car to reach 100 meters per second if it continues to accelerate at the same rate? So here, rearranging is important. So if you look at the equation up here, it's asking how long, and hopefully again, next session when we look at equation triangles, you can get one for this one. But rearranging, you will get T equals delta V over A, the change in velocity over acceleration, which will give you 100 from rest divided by the constant acceleration of 12, and the time will be 8.33 seconds. Hopefully now these practice questions have given you a bit of confidence of seeing how straightforward some of the questions can be, but they're not always as simple as this. However, there are 3 nice straightforward questions here to see how you got on. So quickly, I'll try and stop for maybe 20-30 seconds. If anyone is using the chat, put in some numbers you think you get for the 1, 2 and 3, and then we can have a little look. So question 1, the red car, distance, time, and it's asking for speed. So hopefully you'd use speed as distance over time, and of those 3 values, you would hopefully choose the middle one, 7 meters per second, because the workings would show 56 divided by 8 is equal to 7 meters per second. The second one, using the equation for acceleration, numbers are a little bit more complicated here, not as straightforward. So if you don't have the calculator, you definitely should try and get one ready for your exams. So 72 and 4.5, acceleration is change in velocity divided by time, and you should get an answer of 16 meters per second, showing the workings there. And higher tier, again, it's higher tier because rearranging is important. Not only that, making it slightly more difficult, something should stand out here for you, which is distance is in kilometers. So you would have to identify that 1,000 meters is equal to 1 kilometer. So from that, you should remember that time is equal to distance divided by speed, giving you a final answer of 125 seconds. So hopefully someone's put some answers in the chat. If not, we can make it slightly more difficult, make it more challenging. Let's have a look at some old past paper questions. So these are questions from 2014, foundation tier paper, and we can have a look. In this example, we can see there's a slope where there's a ball rolling down the ramp, and you can see positions A, B, C, D, and E. What's happening in this is you have a diagram where the ball is shown at every 0.5 seconds. So that means from A to B, half a second has passed, from B to C, half a second has passed, and so forth. The length of the track is 10 meters, and every interval is half a second. Calculate, or part A, write down the distance from A to E, so the total distance traveled. First thing you need to do is hopefully identify the total length of the track, which is 10 meters, and identify the number of divisions, the number of notches you can see here. If you can count them all up, you will see there are 9 notches, and each one is worth 1 meter. That will mean 9 times 1 gives you a total distance of 9 meters. Part 2, write down the time taken for the ball to travel from A to E. Again, nice straightforward in here. What you have to remember is from A to B it's half a second, so you need to figure out how many steps are shown. So A to B would be 1, B to C would be 2, C to D would be 3, D to E would be 4. So that means there are 4 time intervals, each one worth half a second. So you would have 4 times half a second, giving you a total time of 2 seconds. So 2 easy marks here, just reading this diagram. How are we then going to use it? So we have a distance of 9 and a time of 2, so we can put this information up here. Distance of 9 meters, time of 2 seconds. Part B, can we use this equation to calculate the mean speed as it rolled from point A to point E? Knowing that the distance is 9 and the time is 2, we can input them and get a speed of 4.5 meters per second. However, the question in part C is asking us to identify and explain how the ball is accelerating. So if we just quickly look back at this diagram, how does this diagram show a ball is accelerating? If you're not sure, what we can do is look and remember that each step from A to B shows a time interval. So for the same amount of time, the distances are increasing. So if we look at this then, what we see is a good explanation would be that the distance between the balls is increasing. If the distance is increasing for the same amount of time, that means the speed must also be getting bigger. Part D, describe how the positions of the ball would be different if the track was less steep. If the track was less steep, that means the acceleration would be less, which would mean the distance would hopefully be a lot less as well. So the less steep the slope, the distances between the balls would decrease. And a final question now before we move on is to look at another 2014 paper, starting to look at some of the higher tier elements. A car traveling at 15 meters per second decelerates to 0 meters per second in 5 seconds on a dry road. Use the equation from page 2 to calculate deceleration. So we have the equation for acceleration, which is just the change in velocity over time. Change in velocity over time. And looking at the information given, we have the initial velocity, the final velocity, and the time. So we can work this out. The acceleration is change in velocity over time, which would be 0 minus 15. It's crucial you understand it's 0 minus 15, not 15 minus 0, because the final velocity is 0, not the other way around. And you get an answer of minus 3. However, in the box at the bottom, we put a deceleration of 3 because that's the value of the deceleration, which is 3 meters per second squared. Part 2 is a bit of a different question because now they provide the equation and it's asking you to calculate the mean speed during that deceleration. And one thing that's always nice to look at here is mean speed is just the initial speed plus final speed divided by 2. Or in other words, the average of the starting speed and the final speed. And the starting or the initial speed was 15, the final was 0. So it's just a question of working out the average of those two numbers, which is 7.5 meters per second. So in the first half of speed, distance, time session today, we've covered the terminology, speed, velocity, acceleration, identifying the differences between the use of the word speed and velocity, looking at the equations for its speed and acceleration, and now we've had a good 5-10 minutes of past paper questions where we get to see some of the uses of them in real life context. Now the second half of the session is going to cover the graphs. Those graphs are speed time graphs, distance time graphs, and then finally looking at velocity time graphs in order to determine acceleration and distance traveled. Distance traveled is in bold because higher tier only are expected to learn the distance traveled and demonstrate it in the exam. So first things first is we want to look at a typical graph. So a typical graph for speed time would look like this, with different elements where we have straight lines with no slope, lines with slopes that are straight, or even gradients that are changing. But we need to be able to understand and describe these features. So when you see a feature such as A, in which it's a constant gradient, in terms of speed time, that means there's a constant acceleration. So at any point along A, the acceleration would be the same value at any other point on A. The line could change by becoming more steep or less steep, and the steeper the line, the greater the acceleration. If we then look at B, what we see is B has no gradient, it's a flat line. That indicates to us that it is a constant speed, and if you follow it across to the y-axis, you could read off that constant speed. That means it's going to stay at that speed. If that line was higher up on the graph, it would indicate the speed is higher. If it was lower on the graph, it would indicate a lower speed. The only special case is if the line is on 0 for the y-axis, it would mean the car is not at a constant speed, it is not moving. That's the only one to be aware of. Part C, if you look at section C on the graph, if I can click it, you can see that the line has a gradient which is changing, and in this case it's getting steeper. This means the acceleration is not constant, and we can see that the gradient is getting steeper, which would indicate that the acceleration would be increasing. If we look at the variations, the line could curve the other way, and again, a good description would be that the acceleration is not constant in that section. D is similar to B, straight flat line along the horizontal, which means the gradient is 0, it's a constant speed, so you can just read it straight off the y-axis. And comparing it with B, you would say that the speed is greater in part D. E, on the other hand, is curving down, but if you look at the gradient and you were to draw tangents or just look at the shape, you can see it's getting steeper. So this is decelerating because you're going from a high speed to a low speed, and the deceleration is not constant because the gradient is changing. And then finally, F is similar to a constant gradient. That constant gradient tells us that the deceleration is constant. And then again, what can be different in other graphs is the steepness of that slope or the steepness of the gradient, which would indicate a greater or lesser deceleration. Speed time graphs are very useful. However, velocity time graphs is where you'll often be asked to calculate many features. If we look at a velocity time graph here that does have data, we can see the same shape as we saw previously, but now we can actually calculate some features of this graph. One of the features you would be calculating is the gradient, or the slope, or the steepness of the line, and we can use that on part A because we know it's a constant slope. So if we click part A, we can see in that section it changes over 10 seconds, and the change in velocity in that time is 20 meters per second. So using the equation for acceleration, we have taken data from our graph, and we can calculate that the acceleration is 20 divided by 10, which is 2 meters per second squared. If you apply this logic to B, you can see we have a problem. If we try using the change in velocity of 0, we'll get an acceleration of 0. So the nice thing about these graphs is you should remember that anytime you see the slope of 0, that means the acceleration is 0, so the velocity is not changing. One issue we would have is if we look at C, it's not constant gradient. It means what we calculate is a mean value. We don't actually calculate the direct acceleration throughout, we are calculating a mean value of that. So again, use the same logic. The time is 10 seconds and the change in volume during that time is 10. So the mean acceleration would be 10 divided by 10, which is 1 meter per second squared. We can do the exact same to part E. It's just change in volume, not change in volume, change in velocity becomes minus 10 over the same time frame of 10 seconds. Instead of 1 meter per second squared, we would have a mean acceleration of minus 1 meter per second squared. And the final one, F, the time frame is 5 seconds here, so quite fast. It's not that clear on the graph, but it's quite fast, 5 seconds to change a velocity of minus 20. So minus 20 divided by 5 gives you a acceleration of minus 4 meters per second squared. Notice how it's not the mean this time. That's because the gradient is constant and not changing. So speed time graphs, velocity time graphs, very useful for us. If you're doing higher tier, you will have to do one additional step, which is to calculate the distance using a velocity time graph. To do that, you have to remember this key feature, which is the distance under the velocity time graph is equal to the distance traveled. So the area under the velocity time graph is equal to the distance traveled. So when we see a shape like this, some of you might see it as a trapezium, which would be very straightforward to calculate if you're confident and comfortable using the rule for trapezium. However, many students also like to break it down into easier shapes. So in this example, we're going to do the straightforward way of break it down into triangles and rectangles. From maths, you should hopefully remember that a triangle is just the width times the height divided by 2, and a rectangle is just the width times height. So we have 3 sections to this graph. We have the first section, which is a triangle that has a width of 10, a height of 10, and when you divide that by 2, you get 50 meters. So in that question, you would have a 50 meter distance traveled. If we look at the rectangle, we have a width of 20, a height of 10, so we get 200 meters of distance traveled. And the final section then would be triangular with a width and height of 10. Do not forget to divide by 2, giving you a distance traveled of 50. So the total distance traveled in this example is 300 meters because you have to add them up at the end. This here, calculating distance using this graph, is something higher tier only. If you're foundation tier, you need to be able to calculate the acceleration from the graph, not the distance. But everyone needs to be able to use distance time graphs. So if we have a quick look now at a typical graph, and this is one of the problems I see quite often is with distance time graphs, a lot of pupils have got the information for speed time graphs in their mind. So here, always check what's on that y-axis right here, because if it said speed, you can use everything we've just talked about. Now, distance time graphs have a different shape, and the shape might look the same, but the descriptions change. So if we look at a typical car journey, the car is moving at a constant speed away from the start, at which point it stops, but the time does not stop. And then it proceeds onwards again at a constant speed until the red light, at which point it stops. And again, notice how the time moves constantly. Once it reaches the petrol station, the car is stationary, it's not moving, and then it begins a return journey back to the start. So a few things that stand out here is that as the as the car is moving away from the start, we call that the outwards journey. So as it's moving from the house to the petrol station, that would be the outwards journey. So any journey away from that zero is outwards. And then as it turns around to come back, we call it the return journey. The shape of the graph is something we need to understand now. Looking at this graph in a bit more detail, we can see that every section here has a straight line. So when you see that constant gradient, that indicates a constant speed. So just here now with a constant gradient, that's a constant speed. When you see the flat line here, that actually indicates that the distance is not changing, just like that car did not move at the red light. So that means the speed is zero. So here, here, and here, these three flat lines, there is no movement by that car, it's stationary, which means there is no speed. So we can work out the speed for any of these slopes, outwards or the return. And because it's a distance time graph, it wouldn't matter which way around we took it, because the distance just has a value, not the direction. So if we focus on one of them, for example, if you have a distance of 400 meters and it took 20 seconds to cover that distance, you would have distance divided by time giving you a speed of 20 meters per second. Another concept that comes up quite often is mean speed. Mean speed is the average speed in that distance. What makes it different is that you just include your whole data. So for example, if the question asks for your outwards journey up to 200 seconds, you wouldn't ignore the lines that are flat. You would include the slope, the flat, the slope, the flat. So here, that total outwards distance would be 800 meters. And that time frame would be 200 seconds. So you would get a mean speed, that average speed of 4 meters per second, which in essence turns that slope, that graph into a straight slope, because it's working out an average. And it is true, if you look at the graph, you can see certain bits are steeper, which would be a greater speed, and there's certain section where the line is flat, which is no speed. So mean speed just gives you a nice approximation throughout that whole journey. So it's 10 minutes left of the session. We've covered the first half now, terminology, the equations. We've now just finished the second half, which is understanding speed time graphs, distance time graphs, velocity time graphs, and how to use velocity time graphs to determine acceleration, and for higher tier, the distance traveled. The final thing we can do now is making sure we can differentiate between the graphs. So here I put 6 graphs up. Again, if you're watching this afterwards, you can pause it to try it out yourself. The PowerPoint should be up on the website so you can work through it yourself. And look at these graphs. Notice how the words are just not in a straight order. So you have to identify, first of all, it's a speed time or distance time graph, and then finally identify what feature it demonstrates. So the top left, the speed time graph, what we have here is a constant slope and the speed is increasing. So when a speed increases constantly, we'd call that a constant acceleration. Move across, this time it's a distance time graph. The shape is the same as the one on the left, but however, we know when distance increases over time, we would see a speed because distance over time is speed, and the slope is constant, so we get constant speed. Next one, we have distance, time graph, and the slope here is 0. There is no slope. Distance here shows that the distance isn't changing. So when there's no distance being moved, you are stationary. Next graph we have here is speed and time. What you can see here is the slope is decreasing, it's going down, so you're going from a high speed to a low speed. High speed to low speed would be deceleration. The slope is constant, so I hope you identify a constant deceleration. Bottom left, speed and time. This time the slope is not constant and the speed goes from a low to high speed, so we have a non-constant acceleration. And in the final graph we can see speed against time, where that speed does not change throughout, so that is a constant speed. So these graphs are hopefully shapes you would be expected to understand, and in past paper examples and past paper questions I have seen 6-mark extended writing and reasoning questions that ask you to describe the motion of a journey using a graph, and then for higher tier, not only describing the motion but also calculating distances under that graph. Okay, again, now we've had some practice with the speed, distance, time and acceleration, change in velocity over time. We can now practice some more full questions, just like this 2015 question, where we have to identify the correct terminology to the correct units. So hopefully now, deceleration, you understand that it's meters per second squared because it's the change in speed. It's the meters per second squared. Mean speed, on the other hand, is just the meters per second. Time we measure in seconds, and distance we measure in meters. So this was a nice 3-mark foundation to your question, which demonstrates the purpose and need to learn the correct terminology with the correct units. The next exam question is what we're looking for now, which is a big velocity time question, a 1-mark question, which is probably part of 3, 4, 5 more marks to do with this. But what we can see is a velocity time graph, which has a maximum velocity of 40, a total time of 80. And when you look at your shapes, you can hopefully see the trapezium, or you could see a triangle, rectangle, triangle. So even if you're sitting foundation or higher, you can already identify things that they could ask you. First question is, write down the time at which the car's velocity was 20 meters per second. So velocity at 20 meters per second, we would look at this y-axis going up here and identify when is the 20 meters per second, and it's here along this line here, if I could draw it correctly. But if that line was straight, we could see 20 meters per second occurs between these two time sections. So what we see here, guys, is better way of animating it, which is the time between those 2 points is between 5 seconds and 65 seconds. So the time between those two would be 60 seconds, but they also accept between 5 and 65 seconds. Use the graph and the equation to calculate the acceleration in the first 10 seconds. So if I go back for a second, we need some information. The information we need is change in velocity over time. And if we look 10 seconds, the change in velocity is 40. It goes from 0 to 40 in 10 seconds. So using the equation, 40 minus 0 over 10, that doesn't look right. 40 minus 0 is 40 over 10, which is 4 meters per second squared. That is definitely not right. So hopefully you guys have a better calculator than the one I clearly used in the exam. If not, I will keep blaming my calculator. So the next paper now is a 2014 paper. Final question we can do, hopefully, before the end of the session. If we look at a car moving at a speed of 15 meters per second, a child runs out onto the road, causing the driver to make an emergency stop. This graph shows the speed of the car from the moment the driver sees the child. What we can do now is look at some of these features. What was the reaction time of the driver? So instantly we want to look at here, how long did it take before the driver reacted? So here we have two distinct sections. We have this constant speed in which the driver hasn't applied the brakes, and then we have the second section, which is where the driver did apply the brakes. And reading off this time here, we can see from 0 to 1, that tells us that each individual element, each individual box is worth 0.1. So the reaction time of the driver is 0.8 seconds. Next question is, how long did it take for the car to stop once the brakes were applied? If we go back quickly, we can see that the brakes are applied when the car begins to stop. So that would be from our point of 0.8 all the way to the end of 4 seconds. So we have 4 minus 0.8, which would give us an answer of 3.2 seconds. The final question, which is what we're looking for, is acceleration is equal to change in velocity over time. Can we calculate the deceleration of that car? We've got the time because the time taken to decelerate was 3.2 seconds. Can we, from the graph, find the initial and final speed? The final speed is 0. The initial speed is 15. So what we get is 15 over 3.2. The acceleration is negative, which is why we put it in here as 4.69, or demonstrate that you understand that the acceleration is negative. Great. There's 2 minutes left of the session. Instead of going on to the next exam style question, I'll leave it open to anyone that's viewing it to ask any questions. If not, I'll pause for a minute just so you guys have an opportunity to write anything that might help. The PowerPoint will be put up on the Carlam website along with this video once it's finished recording, for anyone to watch it back if there's certain bits you want to go over again. And not just that, the whole PowerPoint will be there, so it will include the final part of this question.
Just give it another 20 seconds. See if there are any questions.
Yeah, there's always a 20-second delay, so hopefully if someone is following along, there will be a question up. If not, we've got a nice minute left before anyone else.
I don't know if can I be heard now, or can you only hear me?
I think everyone can hear both of us now.
Oh yeah, okay. Good to know.
Yeah. No questions coming through anyway.
No, we're good.
Perfect. Great. So again, guys, if you are still here and listening, next week will be the second session, which will cover, I think it's equation triangles.
Mm-hmm.
And then the week after that, we're going to look at some graph techniques for the exam. Make sure you get as many marks as possible out of the graphs. And then the final week will be past papers, where we look at some nice past papers to round out the physics sessions.
All right, brilliant. Well, thank you, sir. Thank you, everyone who attended, and we'll maybe hopefully see you again next week.
Yeah, great, guys. Thanks for tuning in.